to make progress. So how do we do things, right? So in the 1970s, then essentially we're coming to the way we program C program and Fortran programming, or even your Python today. Okay, this is 70s. 50 years later, I'm still using this. That's why it's classical, right? We are still doing the same way in terms of C programming and Fortran programming, most of the Python programs. All right. So this is essentially people. In the 70s, people are already proposing how to do things. Basically, a data flow driven programming. Okay, that is naturally come to us because computer is to process numbers. Then number got generalized into data. Data got generalized into information. So we are basically called the IT industry, information technology. Basically, we are processing information, processing data, processing numbers. That naturally, we are a data flow driven industry. Data is the king. If you have data, you can go find programmers and process your data. If you don't have data, you have programmers, yeah, you're going to go into bankruptcy pretty quick, right? So essentially, you need data to fit your industry. I mean, anything, if you have any kind of business, if you look at it, if you have more programmers than your data, you have a problem. Then basically you have to go through layoffs and slim down your team. If you have more data than your team, okay, if that data is valuable to people, then your company is growing fast. That's the IT industry, social media industry, streaming industry, what have you. Today, all these big e-commerce industry, right? Cloud computing industry, what have you. If you look at it, these companies, why they grow so fast? Because they have more data to process, to leverage, to monetize. Then it's come to, if we have the data, abundant availability of data, then we can scale up the team. We need more people like you to work on this data. That's why we have so many computer science students now in our pipeline, because there are just so many data waiting to be processed with programs, not by human. If you process all these data manually by human, it's not scalable at all. So we need people like you who go write programs to process all the data. That's your job. All right. So what is this approach? This approach is essentially take a specification like this. This is very much like our specification we have seen before, and say English spec. Say, okay, how do we deal with this? All right. So this approach is basically say, okay, how we map that English spec into programs. Sounds really familiar, right? That's your job. That's your job. That's your trend for. So essentially, you are trained to be an engineer who take an English spec like this, convert it into programs. A classical method is one method you can use if you are programming in Fortran, in COBOL, in C programming language, right? So you basically ask the question, what business functions should be computerized? How to do it better? In the case of batching, online, in-house or outsourcing, all these things, to be honest, we are not emphasizing these in our class. Okay, what we're emphasizing is here. What business functionality should be computerized? Your program should be able to handle. Okay. So you look at all these functionality. Essentially, you are going to look at cost-benefit analysis and see which part better to be realized by software programs. So essentially, we need to find a solution. Before that, we need to find that problem. So if you have a clear problem defined, which is essentially a spec, you're given a spec, that's actually a pretty good starting point, right? If you're given a spec, like what we have in our class project, it's not that I mean, from there, you can have relatively systematic way to produce something. May not be the best solution, but you can produce a solution. Actually, a more challenging thing would actually be if you have no specification, you have to interview and collect the information. That is going to be actually quite time consuming. If you have a spec, then essentially you can basically conduct stepwise refinement, follow a method, just like object-oriented programming, object-oriented analysis, object-oriented design, and so forth. The same idea. You follow approach, okay, to generate a solution. I'm not looking for the best solution. We're looking for one solution. Okay? We don't want you to be stuck there, looking at the specification and just say, okay, I don't know what to do. This is, okay, yeah, I may not come to the best solution, but I'm going to make progress, moving along, humming along from specification to high-level design into detailed design and writing code. Okay? Maybe somebody else in the class have much better, more optimized solution than you. That's okay. Both of you get 100 points from my project. Because our goal in this class is to get you one solution. And you will have plenty of opportunity to learn how you optimize your solution. Okay? Then certainly when you become more experienced, you can directly jump to a more optimized solution than the one you practice in my class. That's the idea, right? But you can always go back to our approach and say, I mean, I don't know how to do it. I'm just going to write down all the nouns in my specification and make some classes and make some data. Then I'm going to do subtraction and say which one is not needed as I go, right? In that case, you basically keep all the information and only remove certain things when you clearly know it's not useful. All right. So fundamentally, how do we do things? Before we have object-oriented approach, data flow. Data flow, data flow. That is our approach. So essentially, you are following, by and large, something like data flow graph. Okay. So essentially, how your data flows through your system. The notation is fairly straightforward. This has actually already been standardized in your PowerPoint. In PowerPoint, you can create data flow diagram, like flow chart and so forth. Your flow chart, which you did in your homework 1, is data flow graph, right? So what is a data flow graph? You have source and the destination of data. You have flow of data. Then you also have a process that essentially the action on this data and where you go to put the data. Okay? There are no more. All the notation you need for this analysis pretty much appear here. There are one more which you know is useful, going to be you can actually use, for instance, for a flow chart, you have a branch condition. Right? With branch condition, this is enough for you to describe basically all your program. Okay? If you just throw away the hoopla about C++ and Java, all these object-oriented things, once you compile these things down to machine code, assembly level, that's it. You have processing, computation, you have jumps, that's it. Your data store, that's it. Registers, memory space, that's it. Okay? Boil down to, you are doing data flow. Your machine, the data flow machine. The instruction in, result out. The instruction in, result out. Okay? The data flow machine. Our machine, by inherently data flow machine. All these object-oriented approach, they are a nice way to capture your concept. And people were able to come up with all the compilers which map your concept in terms of object into data flow machine in an efficient way. That's your C++ Java compiler. Okay? However, the fundamental thing for computation is data flow. How data flows through your system, where your data is coming from, where is your data process data is going. Okay? Nothing else. Why don't you need loops here? Why on the data flow there is no primitive called loop? Why? In your flow chart, you don't have anything primitive symbol called loop. Why is that?
You can just use a branch.
Exactly. Sequential code plus your branch and jump, you got everything you need for your program. Okay? Loop is basically a syntactic sugar. Make your programming more meaningful to you. Machine doesn't care about it. Machine has no idea you're doing loop, and it doesn't care. Okay? It's you who care about that's a loop. It's you care about this is the array. For the machine, it's just a memory space. Okay? In the machine control flow, you only have condition, jumps, and sequential code. Nothing else. No other thing needed. Your loop can be simulated, your switch can be simulated, all these syntax, higher level syntax, you come up with in Java, in Fortran, in C, in Go. These are just hooklets, make your programming concept cleaner. You can think about bigger things at the same time. Oh, this is an array. I'm going to loop through the array. Right? That's it. But for computer, I don't care. I'm just faithfully executing my sequential code, jumps, and branches. No other things. Okay? That's why, fundamentally, this comes first in our history. Okay? Data flowing through our system. You have source, your process, and your store. For instance, this is one of the first refinement of the system. I didn't have time for you to read the detail, but it's very straightforward. The customer is actually represented by a source of information. Okay? The customer is actually a source of information or destination of information. It is. To the computer, does the computer actually know you? The computer knows a bunch of number about you. Okay? So essentially, the customer is for you. You are using that computer. To the computer, you are just the generator of information, a source of information, a destination of information. Nothing more than that. Nothing more than that. Okay? You can see that this customer is actually represented by a source or destination of information, which in our object-oriented terminology also called an actor. They are just interacting with the system, generating data or receiving data. Display to us, for instance, the display you are looking at right here is generated by the computer right here. Okay? I'm the person who actually gave it input to drive it to different data. All right? So this is fundamental. Then you have a process, basically actions you can do on that piece of data, right? Then you store that information in your computer, either in memory or permanently on disk. Your cloud is basically a big disk for you. Your cloud drive is basically a big disk. Used to be that's your only computer disk, but now it's basically you save to Google Drive. Who knows where it is, but to you it's a disk, right? Or more abstractly, a data store. That's all. Hey, this is actually the model for imdown.com. Same. take a user order, send the back invoice back, and check whether you have it, the customer information, and see if that order can be processed or not. This is essentially the e-commerce model. You may say, oh man, this is creative. No, it's not creative. This is happening in real world already. Just that we use computer to automate this process, right? Can you say that is there anything that Amazon doing today that we didn't do it in the real world? Probably the only thing are going to be the cloud computing piece, right? Because in real world, there's really no such a storage. But have we bought books before Amazon? Yeah. Have you bought clothes before Amazon? Shoes before Amazon, right? Toys. Get services, right? Yeah, we did. So the only thing that happened is we use a computer with networking, huge computing resource and disk to make a scalable system so that we can drive Sears and all these companies into bankruptcy, right? So basically, Amazon is a big store. Customer go in with information, come out with information. And there's another channel, physical thing will come through the mail, through UPS, FedEx, and so forth. Okay? So essentially, for us to look at this, step one is we'll draw the data flow diagram. Data flow diagram is fairly straightforward to understand. It's easier to understand the notation. Doesn't mean that the diagram will always be simple, right? With such a small, simple set of notation, you can actually draw fairly complicated diagram. Can you actually draw the data flow diagram about the whole Amazon.com? Theoretically, yes. Practically, no. Theoretically, yes. Practically, no. Okay? With this simple set of notation. This simple set of notation is basically capture what we do in computing. Only data, process, flow of information. Nothing else. Come back, just if you look at it, this set of simple notation, you can treat this process can be a branch as well. With 4 pieces of notation here, we can capture all computing. Notation is simple doesn't mean the real system is simple. Not at all. Amazon is incredibly complex. I don't know if there is no single person can apprehend everything Amazon doing today. All right. You can keep refining the diagram, right? You can take multiple refinement until you think, okay, we have refined each box into something I can give to my teammate. Go implement. Right? There's no firm formula to plug in to decide when to stop the refinement. I cannot tell you that. What I can tell you is that for notation, for symbols we have, figure we have, sufficient for you to capture all these. But I cannot say when you stop here. What I can say is, you refine this action, the data, into something your teammate can implement. That's the stopping point. That's the stopping point. If that teammate happens to be yourself, you know that pretty well. If it's somebody else, then you better make sure that you use the same notation, and you actually can write down the specification in our document. You can keep refine this, until basically you come to the final, final data flow graph. In that case, you actually can set up hierarchy, divide and conquer. You have system, subsystem, object, functions, and state. Okay? How we deal with larger system? Divide and conquer. How do you keep track of divide and conquer? Hierarchy. Right? You may say, let's build a giant army. Right? There's no commander, just army. Is that possible? No. You have to build a platoon, then build a bigger regiment, and build a bigger and bigger, and basically you have to build in the hierarchy. While you're building the hierarchy, you keep track of information. Right? You partition a big problem into simple problem. What is a simple problem? Each individual soldier can carry out. You guys are soldiers in the software army, right? We partition it to a task in the granularity that you can take on yourself within a given amount of time. All right? Then once we have this data flow graph, then you can say what can be computerized, right? So then what architecture you should be using. So here you can say use a batch machine or a batch process. Then for your bank account, your payroll still use the system batching. Basically, we keep all the record until midnight, and we run them all through. Right? You can use an online approach, right? Like Amazon.com, when you set in an order, so it will come back and say confirm, right? So essentially, you have to look at which one is better. So certainly payroll is still being processed pretty much by batch. Your bank process your information still largely at night by batch. So